The North African countries are economically emerging nations. Dynamic population growth associated with rising living standards and higher incomes has led to a significant increase in energy needs. Most electricity is currently produced from coal and gas, but solar power is set to become increasingly important in the future. In addition to the large-scale solar power stations envisaged in the Moroccan Solar Power Plan, in this region of plentiful solar resources, a multitude of small solar installations will also have a major role to play. Households, businesses and public authorities will be able to produce their own green electricity thanks to photovoltaic systems installed on their buildings. Many people already have solar thermal installations to produce hot water, as can be seen here in Rabat, Morocco's capital. And the government is now paving the way for harnessing the potential offered by photovoltaic systems. The whole country can benefit from this. Solar power can contribute to reducing costly electricity and fossil energy imports and give Moroccan installers and other businesses the opportunity to invest in promising technology which will create jobs nationally. ADERE, the Moroccan Agency for the Development of Renewable Energy and Energy Efficiency, is tasked with promoting renewable energy, energy saving and energy efficiency in the Kingdom of Morocco. One of the activities that we carry out here, which is very important to us, is to show that the technology exists and that it can be used in Morocco. All those involved in construction, from the architect to the property developer, can come and see for themselves here on the roof of the ADERE office that these systems work and that the technology is increasingly reliable, very reliable in fact. Solar power is a key asset in our quest for energy independence, environmental protection and energy self-sufficiency. And today's focus on buildings can be widened in the future to embrace many other applications. This film will take us through the installation of a photovoltaic system by the company AS Solar, showing the different mounting systems available. This installation was financed under the Solar Roofs program implemented by the German energy agency Deutsche Energieagentur, DENA. Morocco is a country with plentiful solar resources and a very long coastline. Because of its proximity to the sea, the country's capital Rabat is often buffeted by strong winds. This factor must be taken into account when mounting solar power systems and, of course, at the planning stage. Thanks to a modern software application, the whole solar power system can be sized and optimized down to the last detail. In no time at all, the components are all ready to be transported to the installation site. In this case, the installation site is the new headquarters building of ADERE, the Moroccan Agency for the Development of Renewable Energy and Energy Efficiency in Rabat. The administration building has large areas available on its roof and walls, making it the ideal place for the demonstration of different types of photovoltaic modules and mounting systems. For almost every type of rooftop mounting, there is a specific system that ensures the safe and professional installation of all these valuable PV modules. Given that a high-quality PV system has an expected lifetime of over 30 years, at the planning stage, it's essential to make sure that all the elements will be able to withstand climatic and environmental conditions for that length of time. It all starts with the mounting system. Skimping on this item to save money is the wrong way to go. In fact, compared with the cost of the modules and the inverters, the cost of the support structure is minimal. The main challenge here is to design a high-quality static support structure capable of withstanding the violent winds that can affect the region. When planning a system that has to last 30 years, weatherproofing is an important factor to be taken into account. The parts used in most mounting systems are made of aluminium and stainless steel. If plastic parts are used, they must be especially resistant to UV radiation. The type of roof where roof mount systems are most commonly installed in Morocco, both on individual dwellings or blocks of flats, is the concrete flat roof. Let's now look at 3 examples of modern photovoltaic systems adapted for placement on flat roofs. Particularly noteworthy are the aerodynamically optimized photovoltaic systems specifically designed for flat roofs. They don't need to be secured to the roof, and ballasting requirements are low. Generally, wind loads acting on the surface of the modules generate uplift forces. In ordinary installations, this pressure has to be countered by significant ballasting or mechanical attachment to the roof, which means penetrating the roof covering. These systems, which have been in use in Germany for a long time now, are based on an aerodynamic principle similar to that employed by a car spoiler, the flap fitted to the back of a car to reduce lift. It's important to follow the manual closely step by step. The solar modules must be moved and mounted carefully. Care must also be taken not to step on the solar modules or place or drop anything on them. Here is the Schlatter Allu grid mounting system. First, the mounting rails are put in position. The fastening clamps onto which the modules will be fitted are simply snapped into place on the base rails. One of the advantages of the Allu grid mounting system is that installation is virtually tool-free. The special fastening clamps are secured by firmly clicking them into place and can easily be removed with a screwdriver should they need to be moved. The fastening clamps and cross rails, which can be adjusted individually along the base rails, are positioned at intervals calculated beforehand to avoid module shading. The wind deflector is then fitted to the back of the rack and is securely attached to the rails using fastening clamps. The module can be tilted by either 10 degrees or 15 degrees. The wind deflector sheets can be joined to each other using connector plates. The lower edge of the solar modules is placed on the cross rails and securely attached using fastening clamps. The same procedure is repeated for the top edge, which is secured to the wind deflector. Lastly, the metal tabs are bent around the module frame so that the wind deflector is secured in place to achieve the spoiler effect mentioned above. The special clamping pliers supplied with the kit must be used to tighten the module fastening clamps. The cable clips are fastened to the wind deflectors. The stones supplied with the kit are then placed in position as shown in the ballast plan. The MSP FR mounting system developed by the company Hilti is also an aerodynamically optimized solution in which ballasting requirements to reliably secure the system are low. The slightly raised structure with a wide base has the advantage of permitting generous airflow under the modules to dissipate heat and of preventing the accumulation of water in the event of heavy rain. The first step, as always, is to position all the parts on the rooftop and screw them together. The rails supplied are secured to the feet using the appropriate screws. It's important to always use the screws specifically indicated for each part as set out in the manufacturer's manual. All screws must be tightly fastened. During this assembly process, it's important to ensure that the feet and connectors are correctly spaced as shown in the instructions. Along with the standard rails, ballast trays are also fitted. Weights, such as bricks, are placed on the ballast trays to weigh down the structure as required. The exact load can be determined by consulting the site-specific ballast plan supplied with the kit. The modules can then be mounted and secured using the special module clamps.
Deshalb sind die so locker ausgeführt.
Lastly, the wind deflectors are fitted to the back of the rack and secured with screws. As this is done, each module is automatically grounded as the threaded screw penetrates the module frame, piercing the anodized coating to create a conductive bond with the rack. Each PV module rack must be grounded in this way. Care must be taken to ensure that all the metal parts of the rack are connected to each other to create a conductive bond. If standard PV modules with aluminium frames are used, these frames must also be grounded. In Morocco, as well as the large number of flat-roofed buildings, there are also many buildings, particularly industrial warehouses, with corrugated or trapezoidal sheet roofs. For this reason, let's look at a mounting solution specifically designed for roofs of this kind that is optimal in terms of cost. First, the mounting rails are fastened to the trapezoidal sheet roof. This is done using the single-fix fastening system. The roof clamps are fitted by simply slotting them into the lower groove on the mounting rail in the required position. The single-fix fastening kit, specifically designed for trapezoidal sheet roofs, comes with self-tapping screws and sealing washers. The drillings made to attach the fastenings are made watertight as they are secured, thanks to the rubber lining inside the clamp and the sealing washer fitted with each screw, preventing any leakage through the roof. When PV systems are installed, one of the factors to be taken into account is linear expansion. All materials expand when exposed to heat and contract when they cool down. The thermal expansion coefficient for aluminium is relatively high. Based on an empirical rule, an expansion gap of at least 2 centimeters must be left every 10 to 12 meters to allow for the expansion of the metal. The mounting kits are slotted into the upper groove of the rails at the required clamping points, serving to temporarily hold the square nuts in place. The solar modules can then be mounted. They are secured to the rails using the appropriate middle and end clamps. The free ends of the rails are then closed off with a plastic cap. This mounting system is particularly suitable for flat roofs made of resistant concrete with sufficient static load-bearing capacity, as the system can be secured solely by ballasting. Attachment to the roof is not essential, avoiding damage to the roof covering. The advantage of this type of mounting system is that it can be installed very quickly and easily. Furthermore, the system is totally flexible as each module is mounted on its own rack, making it relatively easy to change its position. This mounting system can be used on roof surfaces with a maximum pitch of 5 degrees and also on open ground. The first step, of course, is to determine module spacing to avoid any shading. Bricks, concrete blocks and coarse gravel can be used for ballasting. Whichever is chosen, it's important to use the prescribed amount specifically calculated for the site in question. Once the plastic tray has been correctly positioned and ballasted, the PV modules can be mounted. Before the modules are mounted, 2 aluminium rails are fitted onto the back of the module and then secured to the plastic tray using clamps and screws. Lastly, the Console Plus rack is fitted with a streamliner, a back cover that acts as a wind deflector to reduce wind loading. Rooftops are not the only option for the installation of photovoltaic systems for the production of electricity. If the roof area is too small, solar modules can also be installed on the walls of buildings. Ideally, the wall should be south-facing and not overshadowed by any nearby buildings or trees. The photovoltaic modules can be installed parallel to the wall or tilted to the optimum angle. When choosing the mounting system, static data must be taken into account, as the forces acting on the modules will undoubtedly be transmitted to the wall of the building. We can see now an example of how the mounting process can be carried out. Triangular supports are secured to the outside of the building at the points indicated in the mounting instructions. Deep holes must be drilled into the wall for this purpose, because here too, the PV system may have to withstand high wind loads. In the case of clad walls, a hole must first be made in the cladding using a drill, through which the 4 holes required to mount the structure can be made with a hammer drill. A 2-component adhesive is used here. First, all dust and dirt must be cleaned from the holes using a small manual air pump and brush. This is a very important step in the process, as it is the only way to ensure that the adhesive sets properly. Once the cleaning process has been completed, the adhesive is put into the hole. A threaded rod is immediately inserted before the adhesive paste has time to dry. The triangular supports can now be directly mounted onto the threaded rods.
هذا
The crossbars are then mounted, threading the screws through the slots to secure them to the triangular supports. The modules are mounted on the crossbars and secured using ordinary clamping systems. In the case of frameless glass solar modules, special clamps must be used to avoid breaking the fragile glass surface. These laminated clamps are rubber-lined and should not be fastened too tightly. The open ends of the crossbars are closed off with plastic caps, as in the roof mounting system. If framed PV modules are used, care must be taken to ensure that the frames are grounded by creating a conductive connection between the frame and the rest of the mounting system. In the case of Schlatter mounting systems, the module frames are grounded thanks to special module grounding clamps. The clamp grip has 2 small metal pins that penetrate the fine anodized coating of the aluminium frame when the clamp is tightened, creating a conductive bond between the frame and the rest of the mounting system. A single middle clamp is sufficient to ensure the grounding of 2 modules at the same time. In cases where the roof area is already occupied by other equipment, such as air conditioners, a PV array can be mounted on a raised support structure. One advantage of a pergola-mounted system is that it provides a pleasant shaded area underneath, which is a plus when the roof is used as a terrace. This type of structure rests on poles made of zinc-plated steel. The lengthwise profiles are made of a special kind of aluminium, enabling them to span longer distances. In the preparatory phase, the lateral supports of the structure are attached to the supporting poles, and then the lengthwise sections are put in place. They are secured in such a way as to ensure the required stability of the structure. The exact positioning of the supporting poles on the roof becomes clear once the support structure has been assembled, which is why it's not until this time that the poles are secured to the roof. The same procedure is used to secure each pole. 4 holes are made in the roof with a hammer drill, using the pole as a drilling template to ensure that the perforations are made in exactly the right place. The supporting poles are secured using an adhesive paste prepared by mixing 2 components together immediately prior to application. This way, wind loads are directed towards the roof and the roof surface is waterproofed. All drilling dust must be cleaned from the holes using an air pump and a brush, and then the air pump again. The adhesive paste is then placed inside the holes. Before it can dry, the lower ends of the supporting poles are secured using threaded rods and nuts. Once the supporting structure has been erected, the isotop triangular supports are pre-assembled on the ground, where it's easier to work. Now we're going to assemble the triangular supports for our solar pergola. You can see them already mounted here, ready for the next step in the mounting process. We're now going to assemble them directly on the ground. You see, it would be more complicated to screw all the parts together up on top of the pergola. There are lots of small parts involved too, so this job can be done much faster and much more efficiently on the ground. We've already assembled all these parts here, and we work as if it were an assembly line. There are 2 or 3 specific instructions that need to be followed here. The positioning of this part and that part. This support at the front is asymmetrical, so that it can be centered when it's assembled.
Damit man es beim Zusammenbau zentrieren kann.
The triangular supports are now secured to the structure using the kick-top system. When the mounting system is being installed, it's important to get the spacing between the triangular supports right to make sure there is enough room to mount the solar modules and to avoid shading. Once all the triangular supports have been mounted, the crossbars are then secured. The solar modules are then directly mounted on these crossbars. The supports are assembled lengthwise using the corresponding fasteners and tightly screwed in place. Once the support has been secured, the thin film solar modules can be mounted. This is done using the same clamps as before. And again, in order to ground them, special grounding clamps are used with metal pins that pierce the anodized coating to create a conductive connection. When the modules are mounted, it is essential to align them in a perfectly regular layout in parallel rows. This ensures optimal use of the space available. Once mounted, the modules are connected to each other as shown in the mounting instructions to form strings. When laying the cables and connecting them to the modules, it's important to ensure that the cables are not connected in conductive loops, with a view to limiting the risk of induction voltage peaks in the event of a lightning strike. The cable specifications stipulated in the mounting instructions must be strictly followed, paying particular attention to cable diameter. The positive and negative pole of each string is connected to the inverter via a connecting cable. When choosing the materials to be used for the installation, it should be borne in mind that PV systems have a long lifetime. Particular attention should be paid to the resistance of plastic materials when exposed to sunlight. For example, wiring should be carried out using special solar cables. This type of cable is specifically designed to be UV resistant so that it can withstand prolonged exposure to sunlight. It also has two insulating sheaths, and the core is formed by strands of tin-plated copper wire capable of withstanding up to 1000 volts. To avoid damaging these protective outer sheaths, care must be taken not to route cables over sharp or protruding edges unless they are first fitted with edge protectors. All cables must be laid in the cable channel without applying excessive pulling force and taking care not to bend them beyond the specified minimum bend radius. Additionally, in order to ensure that they last for their expected lifetime, all the cables should be tied together, particularly when they are fastened to the rack. Over time, cables can become worn if the effect of the wind causes them to rub against sharp edges. It is essential that any cable ties and clips used are also UV resistant. For the wiring of a PV system, there are a variety of special cable plug systems that can be used depending on specific requirements. Cable plugs that can be installed without crimping tools are particularly practical. For the protection of both users and the installations, the entire structure must be grounded or connected to an equipotential bonding grid. For the grounding of different types of racks and modules, all the parts of the racks must first be connected to each other to ensure conductive bonding. A ground wire with a cross-sectional area of 16 square millimeters is then connected to at least one point on the rack. In order to avoid running too many ground wires from the roof to the inside of the building, it's recommended to bring all the cables together on the roof and then run one wire from that point to the building's ground connection. A special bus bar has been used to ground the installation, bringing together the ground wires from all the devices and all the metal racks. To check that the grounding system meets local technical regulations, an electrician has to take the required measurements and record them on a certificate. To prevent any wiring errors and to facilitate system maintenance by the operators who will eventually be responsible for operating the system, it is essential for all cables to be carefully labelled. With outdoor installations in particular, it's important to use lettering that will remain legible for a long time, even when exposed to the elements. To prevent mislabeling, it's recommended to label each cable as it's laid. All the modules are now firmly secured and correctly wired. The next step is to install the power electronics and hook the system up to the electricity grid. Inverters are required to convert the direct current produced by the PV modules into an alternating current which can be fed into the electricity grid. The inverter must be compatible with the photovoltaic modules in terms of its technical characteristics and the way the modules are interconnected. First of all, it's necessary to decide on the best location for the inverters. Most high-quality inverters are designed for use with equipment with a high protection rating, such as IP65, and can therefore be installed outdoors without any problem. However, it's recommended to hang the inverters in places that are as cool as possible so that they can dissipate the heat that they generate. Well-ventilated, shaded locations are recommended. When hanging the inverters on a mounting bracket, it's important to comply with the clearance requirements stated in the mounting instructions. Room must be left at either side, 30 centimeters for example, so that the inverters can expel hot air from the sides. A further 50 centimeters clearance should be left underneath the inverter, simply to ensure that there is enough room to work comfortably and so that the cable running down from the inverter can be properly positioned. The first step is to wire the inverter on the alternating current side. Each inverter must be fitted with an independent circuit breaker to protect against short circuits. The inverters are protected from voltage surges from the public electricity grid by installing a Type 2 surge protection device on the distribution board on the AC side. Surge protection for the photovoltaic installation must be adjusted to the building's surge protection. Depending on the size of the photovoltaic system, when wiring, the inverter outputs can be regrouped in separate sub-distribution boards. When hooking up the grid, care must be taken to ensure that the load is distributed as symmetrically as possible for each phase. In the installation shown here, the outputs from 2 of the 6 single-phase inverters are brought together and distributed in one phase. When the wiring has been completed on the inverter side, the connection to the grid can still not be activated. It can only be activated after the DC wiring has been completed and the inverter is in operation. The next step is to connect the DC cables from the module strings to the corresponding inverters. In order to protect the inverters and the domestic electricity network from possible damage to the PV system caused by lightning strikes, a Type 1 DC surge protection device with a lightning arrestor must be connected between the PV modules and the inverter. Lastly, before the DC wiring is connected to the inverter, its performance must be checked again by measuring each string and verifying the polarity and voltage to ensure that they are correct. The voltage is correct when it corresponds to the number of modules connected in series. It is compulsory to record the values measured in the installation documentation. As with the outdoor wiring, the cables of the distribution boards and those connected to the inverters must be labelled. Only when everything has been checked can the integrated switches be connected, in the case of SMA brand inverters, the ESS handle. After a brief automatic inverter system check, the inverters start working.
93 Volt.
At this point, the inverters can be connected on the AC side. All the important parameters will then come up on the electronic displays. There is another important safety warning to be heeded at this stage. When carrying out any maintenance work on the electric system of a PV installation, the inverter must be disconnected. Opening the AC fuses alone is not sufficient because the DC side remains live. Special care must be taken when handling the DC cables. They must never be left unplugged when the system is live. Very high voltages can cause arcing, as seen in this laboratory test. This is very dangerous for anyone working on the electric circuit and can damage the cable plugs. A small weather station with a solar radiation meter transmits real-time meteorological data. Installing a weather station of this kind is useful, for example, for making an accurate comparison between theoretical data and real data for a PV system, to monitor performance and to provide documentation relating to the warranty. If the system operator considers that the data shown on the inverter displays is not sufficient, the installation of a remote monitoring system is recommended. With this type of system, all the inverter parameters are displayed and can be consulted from anywhere in the world using the internet. The main purpose of a remote monitoring system is to display and transmit fault messages. It is not so easy for an operator to notice that one of the inverters is malfunctioning and has stopped feeding power into the electricity grid because they work noiselessly and are often located separately in a service room. Such a system is obviously of great interest in large-scale PV installations because larger investments are involved. In the event of a failure, fault messages are sent by SMS and email to the operator or maintenance company responsible for the system, who can then go to the site and resolve the problem. A remote monitoring system also provides a number of other functions and options. For example, the updated technical characteristics of the installation can be downloaded onto a smartphone. In addition to this instructional film, ADADE can also offer you training in a number of areas relating to renewable energy, such as individual and collective solar water heaters, grid-connected photovoltaic systems, and energy efficiency in buildings and industry. In the photovoltaic sector, the Marrakesh Training Center is ideally placed to deliver continuing training, with the pilot PV installations and experts in this field ensuring a successful learning experience. The center gives engineers and planners the chance to enhance their knowledge of photovoltaic technology and system sizing. Installers and technicians can take advantage of training opportunities in system installation and commissioning, and can benefit from training that focuses on practical skills. For decision makers and stakeholders, ADADE also runs customized introductory seminars offering practical guidance on this subject. Particularly in countries with plentiful solar resources like Morocco, photovoltaic energy is one of the main alternatives to conventional electricity production. Solar power is clean energy and is available in virtually limitless quantities. The conditions now in place for feeding photovoltaic power into the public electricity grid have broadened the outlook considerably. This new framework is opening up the photovoltaic market and providing significant growth opportunities for small grid-connected systems, along with the creation of employment opportunities for well-trained people.